right, Dean and Gavin, welcome to the video. They've been working for a little bit in their groups on the problem on the board. There you go. I gave them a hint that this is a problem after section 6.1, so using Riemann sums. They're having a few issues thinking about how it is technically a volume question, and yet there is a way to approximate with sums the volume similar to section 6.1. I've heard things like n equals 8.
Half of a sphere. Hemisphere.
You can hear them saying hemisphere in the background.
True.
We're going to go ahead and go see what they were able to come up with and how close it is. If you want, you can pause the video to think about it yourself just a little bit as well. Play around with the problem. Not a bad idea at all, but right now I'm going to check in with them and see how they're doing.
In fact, it is infinite because you can just draw straight down.
From geometry.
No, if you're drawing symmetrical lines in a square.
All right, let's see what you guys were able to come up with and whether anyone thinks they have a solution, knows they have a solution, etc. Let's unfreeze this screen. Yes, make sure you have a color pen out. We're going to be grading 6.1 in just a second. And finishing 6.2. So, you're supposed to be estimating, so it's not the exact. We're supposed to be using discs and washers per se. Estimating the volume of a solid hemisphere, solid, so it's like an entire half sphere. You guys get it?
Yeah.
Okay. Of radius 4, as you guys can see, shown by the picture. Imagine the axis of symmetry on the interval 0 to 4 is the x-axis, so it's perfectly around the x-axis. But we can tell that from the equation. I mean, that's not a super big deal. And then it keeps going from there. What do we know? 8 subintervals, equal length. Approximating with cylinders. Whoa, what? Cylinders? How did that come about? What's happening to those representative rectangles? They're spinning, right? And as they spin, what do they form? Sorry, my remote is missing, and I need to unfreeze the screen before I can write.
A cylinder.
I literally just did, and it froze again. Oh, thanks.
Oh, never mind.
Depends on the day. There you go. Okay. So, why is it a cylinder? Each of those little markings that you guys see is a complete sideways view of a cylinder. A very, very flat cylinder, but a cylinder nonetheless, right? Okay. And it says that the subintervals left endpoints. Good? So we have left, and we have n equals 8, and we have using the cylinders to approximate the volume, and we have this clue of y equals the square root of 16 minus x squared. So, just for sake of argument, I know, none of us want to actually write this, but just so we have the idea, there would be 6 volumes, right? What do we have to remember in order to do volumes? I know, we'll find a pattern. We're lazy, I get it. Base times height, no, it's volume. Oh, pi r squared h. Oh. So volume is equal to pi r squared h because we're not like taking an area and plugging it into an integral to find a volume. We're actually finding the volume of all these little three-dimensional cylinders and adding them all up to get an approximate. And this is the math that would be necessary for, remember last year how we were doing discs and washers and I showed you that one calculus class that did the project of like the raindrops and then like the snowman and then like the shark.
Yeah.
They actually did math of, okay, what volume is symbolized by this little fragmented approximation with discs and washers. And then they did the calculus to say what it was exactly and how far off they were, etc. That's what we're doing. We're seeing, okay, if we were to have these solids, about how close would it be? Well, we're not seeing how close it would be, sorry. What would the volume approximation be? So we have pi r squared h. What's changing for each and every one? The radius is changing because 4 is only for this one. Doesn't the radius change every single time? What else is changing? Radius is this guy, right? And isn't that getting shorter? But what's not changing? The depth. Because check it, what did they say about the subintervals? They're equal. And so we've taken 4, we've cut it into 8. So what are each of these say, okay, for each of these, aren't the pi's going to be the same for all, right? And then, the r's change. But then aren't the depths or the heights going to be the exact same? Now, this one I could put a 4 in, but that's not going to help me because then I have to actually find the next one, the next one, the next one, the next one, the next one. I want a pattern, don't you? Throw it in Riemann sum, throw it in our calculator, be done. So how am I going to figure out my r? Plug it into the y equals, because isn't the y the height, but the height in this context is the radius, right? Yeah. This is the radius. The y is the radius, and the radius keeps changing. This is still a radius, but it's also still a y. So I want, wait a minute though, it said left, true? Okay, so I want to plug into square root of 16 minus, oh hey, square root squared, I mean that's kind of nice. So I can actually just have square root squared, 16 minus, okay, so how would I do this if I was trying to throw it into a Riemann sum? So I have n equals 1 to 8. I have pi times, if you want, you could do square root squared, but why not just simplify our lives, right? Okay, do I have the height for every single one? The depth? Do I have the pi r squared, square root squared, canceled out? Yes. Now, how do I get all of my left endpoints? I need it to start at 0 and then go all the way to 3.5. Yeah? I mean, we could do 0 plus, a plus, but I mean, 0 plus is just itself. So forget the 0 plus. How do I get the left endpoint again? 0.5 times n minus 1. Would that work? 1 minus 1 is 0. I start at 0. 2 minus 1 is 1.5. 3 minus 1 is 2.5s or 1. And then 1.5, 2, 2.5, 3, 3.5. Got it. Plug in the last one. 7.5s would end at 3.5. That's my last rectangle. My last cylinder. Got him. What's my final volume? So that those of you guys that did it a different way can also check. Who's throwing in the Riemann sum for me? Someone. Check Abby. Anybody else getting 347.146? No, I think you're right. Hold on. Double check your parentheses though. So see the squared. Oh. That shouldn't make a difference. So 16 minus this squared. Technically, a parenthesis belongs there. Okay. And pi r h. Oh, hold on. 146.084.
Got it.
Got it. Because the parenthesis. Oh, I see. If you took this parenthesis out and moved it, this would have only been times him. They would have had to go into both or just be on the outside. So in a way, you kind of like deleted this parenthesis and moved it out.
Oh, okay.
Which changes the meaning. Sorry, 146.1?
146.084.
And that would be in, oh, did they give us any units? I don't think so. Something. Units cubed, whatever it is. Sorry, question.
So how would you know if like the cylinder was sideways like that and not like just going straight up?
Because of the context that they explained to me that this was a hemisphere, so half a sphere, so I knew that this was a three-dimensional figure, so it wasn't just the rectangles that I saw. And then it also said cylinders, so I knew that that sphere was being comprised by little discs, like technically. Where is it? Oh, where is it? Ah. I know I call these discs, right? But discs would be infinitesimally thin. This is technically a 30-foot lattice. Does that make sense? So it's weird in our heads, but what you're seeing is just like these little rectangles. But in context, to make that hemisphere, they had to be little cylinders that we call them discs. Does that make sense, guys? And what we do when we go through an integral with discs to find volume, which only because you guys know and you've been there, is we take this pi r squared, but all of these h's that give us that error, that jut out from the actual perfect smooth boundary, we make this dh, or technically it'd be like a dx, or in this, yeah, it'd be a dx in this case. And that way the integral makes these infinitesimally thin by accumulating all of those limit to infinity there was more to the question, guys, but the long story short, I was trying to see if you could kind of take the idea of Riemann sum and apply it to something different, accumulating volumes instead of accumulating rectangles. It says find S of 8. We got it. That's what's over there. What do you guys think? Would it be an overestimate or an underestimate? Over. And if you want to, I mean, we can be really snarky and be like, we know how to do this. 0 to 4, right? Pi, and then we could have thrown in our r, square root of 16. So if you guys want to, you can throw it into your actual calculator. But why would we assume that it would be an overestimate? Because my function is decreasing, which means a left decreasing, yeah, is decreasing. The concavity doesn't matter. Whenever my function is decreasing, left will always jut out above. Right will always jut under below. Anyway, they didn't actually ask us to find the actual, but I'll just throw it out there. Okay, so our goal today is to go ahead and get into definite integrals and talk about him more. But first of all, don't you have a 6-1 we should grade? I gave you a few evens, I do believe. Number 2 and number 4 were kind of like concepty, I think. Number 2 and number 4 were kind of concepty, I think. Let me give you a second. One of them was literally looking at the area and seeing that it was a trapezoid. And then just using the area formula, you guys have to remember the area of a trapezoid. We're not doing trapezoidal sums yet. We're not doing trapezoid like Riemann sums, but literally it was a trapezoid because you had that linear rate. You had that linear rate. And so therefore you could draw the line. The area would be a trapezoid. 1/2 height times base 1 plus base 2, or 1/2 base times height 1 plus height 2, depending on your brain and how you think about it. It's 1/2 times the whatever's staying constant, and then the sum of whatever's changing. And number 4 was a linear rate also, right? So also a trapezoid. So 20 for the first one and 42.5 for the second one. Now guys, I gave you these two because if it's a constant rate, I know you can do distance equals rate times time. It's a simple rectangle, but as soon as you have a linear rate, well, things get a bit more complicated without integrals, but they're still geometrically possible to solve. So I gave you linear ones because they're trapezoids. You could use area. Some of you might have just used an integral, but that wasn't the point. Number 8, I think you're supposed to do just RRAM and MRAM, or LRAM too? Oh, I guess just those two. Let me try to get it.
Number 7, that's one. Right.
Are the numbers wrong?
No, basically 8 was like using the information from number 7, doing right RAM, and then.
Oh, got it. So you're looking at the 1.25 for the RRAM and then 1.375 for the MRAM. MRAM should be a better approximation. Yeah, definitely is, because this one you don't even have anything approximating, because coming from the right, that's a 0. So MRAM is definitely a closer approximation. Number 20. You're finding the LRAM and the RRAM and finding the average. And then number 26 was just an LRAM ending up with 31.416. think that's our last even. Oh, nope, we have these little baby ones at the end. Lo siento. They're asking for units. On number 32 would have just been millions of units because the per year and the years cancel out. And then 36 is D and 38 is D. When you guys are done grading, I do have the book open if we do have questions, but sorry, a couple more seconds in case you need to grade. Scroll up to which one? 20 what? Oh, there you go. Yeah. Number 20, I think, was trying to make the point that the average of the LRAM and the RRAM are... do I want to do that? They're not always the same as the midpoint, which is awkward and weird in our minds, but it's because the midpoint height is not always the average height. Average height is what you're doing right here between the left and the right, but that's not always exactly where the midpoint of the subinterval hits. Averaging these two is not the same as the midpoint, sadly. But any odds or evens that we want to see on 6.1? Really? Riemann sum homework we're totally good on? Yeah. 5, okay. Let's go check out 5. If that's the only question, then let's just look at it together as a class real fast before going to section 6.2. If you guys are bored and just chilling, 6.2 is already on the website. You could copy down the homework. A particle starts at 0 and moves along the x-axis with velocity. Oh, it's a curved one. So it's not just a linear one where I could use a trapezoid. It's a curved one where we have to use calculus. Oh, well, hold on. They don't want us to use an integral yet. That's why they tell us to approximate the area, right? So in context, we're trying to figure out a change in position that occurred. Maybe for a bigger context. I don't remember. What does it say? Oh, it says where's the particle at for. Oh, the AP guys, though, they would have made it way trickier with an initial position. This looks a lot like one we did. But I don't think we used the rectangles to approximate. So t squared plus 1 is a parabola shifted up 1. We're going between 0 and 4. This is our velocity. And we're trying to approximate with 4 rectangles equal width and height. So if they're equal, then can't I split it up in 1 and 2 and 3? Hey guys, I love that you guys want to talk to each other, but now is not an appropriate time. If you're bored, get into Google Classroom and write down the homework from section 6.2. I think I even took pictures of that. You can even start the homework if you want. Something to do with last year and shake out, I don't even know. So, midpoints. Midpoints mean when we go to number 5, Abby, our area, which is the same thing as our change in position in context of the problem. It's going to equal, well, all of them are going to have bases of 1s just because I'm splitting it myself and I'm going to split it evenly. Pretend that's even, right? So all of them have bases of 1s, but the heights, well, this says determined by the midpoint. So how high do I go? Here? No, that's the right. Here? No, that's the left. I go, the middle would be 0.5, yeah? I need to go hit the function at 0.5 and at 1.5, 2.5, 3.5. So I'm going to have f of or v of. So you have options. One option is you can figure out how to write this as a Riemann sum, but to be honest, at this point, I think I would have just thrown y1. I would have thrown that t squared into my y1, and I would have used that cool little option in my calculator to do y1 of. See what I mean? Just saves a little bit of time from the Riemann sum. Did anybody do a Riemann sum for this one though? Were you guys practicing on that last night? Did you write it out for them?
I wrote it out.
Yeah, what'd you get, Ken?
I kind of just left it stick it to the man.
Yeah.
Okay. 1/2 and then squared plus 1 plus 3 over 2 squared plus 1 5 over 2 squared plus 1.
Oh, got it. So you didn't necessarily summarize it in this, but you literally just kind of did I know 1 times anything is itself. So then he went ahead and just said like, hey, let me plug it in, and then let me plug it in. So he's actually plugging in 0.5, 1.5. That should land us smack dab into that last of it. Is that cool? Alright, that was number 5. Last call for questions. Going once, going twice. Sold. Let's go play with section 6.2. Yesterday we wrote down a Riemann sum definition of an integral. We wrote down a definite integral with the bounds and the integrand and the variable of integration, that differential at the end. I think it was in our forever card last year that we showed the alternate part of the definition of the integral with the partition. I don't know if you're going to need that for the AP. Maybe in a review. I think I show it because sometimes they do it that way. They could also have this, which is really awkward. But this is notation for the partition going to 0, aka the distance in the subintervals going to 0. As you notice, every time we do a Riemann sum, we have actual subintervals of actual width. But the more and more rectangles we fit in, the thinner and thinner those subintervals become. The partitions or the widths of those subintervals are going to 0. It's another way of showing basically the exact same thing. And that would be, I think we could still do it with a equals 1 to n. That would c sub k delta x. Just instead of saying let's let the n go to infinity or the partitions go to 0. I think the formula might change a little bit in the inside too, off the top of my head. I don't remember exactly where we put it because the partition isn't explicitly shown in the definition. But anyway, there are kind of 2 different variations to the limit definition of the derivative. We just need to be aware, need to be on the lookout. But they are not going to ask us, as far as I've ever seen or heard, they're not going to ask us to write out the definition. We just have to recognize it. We just have to recognize when it comes and what it shows. So remember, whatever shows up, whatever function shows up, that's the function whose area we're trying to find underneath, aka the function that matches up with the integrand. The a and b would have to be given to us as clues apart from the limit definition, because this definition does not show me the a or b unless they actually start plugging in. Let me use the more traditional limit definition. We would see a if they actually did, like a number plus, if they were actually showing us that partitioning. You could do your delta x times k. If they actually showed what we were doing yesterday as far as multiplying. These little partitions, these little subintervals, if we were multiplying the widths and then we were adding to the initial, like maybe we could see a that way. The problem is we wouldn't exactly know where we wouldn't exactly know where b is though, because we wouldn't have like an ending point to look at. So this a and b, it needs to be given either in a picture or in context, like of a word problem. They have to somehow give us those a and b clues. Maybe we can see a depending on how they write it, but b has to be given to us outside the definition, which is kind of awkward, kind of weird, but still a thing. I guess we could see it if they did b minus a over n, if we could actually see that work, if they kept on plugging in. Anyway, who knows? Maybe they will, maybe they won't. We'll keep an eye open on our forever cards. But let me peek ahead really fast because we have done a lot today, and I think I'm going to skip solving this integral using a triangle. I'm going to skip this for right now. It's a really cool activity. It's a really cool exercise. Maybe we can peek at the beginning of tomorrow. If you didn't see it was a semicircle, is there a mathematical way of anti-deriving this? Anti-deriving? No, but a workaround that uses a triangle? Yes, but we don't have time right now. So instead, let's finish up the basics of section 6.2. Basics like, Ryan, was this your question about area and how can it be negative?
Oh, yeah.
Yeah. Pay very close attention to how they're wording it. They're not saying positive area, negative area. They're saying area above and area below, and they're putting area below after a subtraction sign. So they're not saying that area itself is possible to be negative, but they are saying we will assign negatives to area, which in context mean negative change. Cool? So the integral from a to b of f of x dx is the area between a curve and the x-axis. Yes, but remember this whole idea about area above is going to be positive displacement or positive change. And then area below is going to be negative change, which is why we assign negatives to those areas that we find and or are given. Well, if we're given, oh, that's hard. It depends how it's given, whether we're making it negative or we're keeping it negative. That's a better way of putting it. So, if we were trying to go from 0 to pi of, oh, can I make that any bigger? You guys might not be able to see it. If we were going from 0 to pi of sine of x, hey, that's the guy whose graph we're given right above. If we were given that the integral from 0 to pi of sine of x is 2, can you guys use that fact to solve for all the rest? Oh, this is dumb. You can just do an antiderivative. The antiderivative of sine is negative cosine. And plug it in, plug it in. Yes, I know, but you know the AP. They're going to say the integral from 0 to pi of some random f of x is 2. And then solve. I'm going to zoom in. So, if the integral from 0 to pi of sine is 2, how could we bust out each of these? You guys don't have to necessarily worry about all of the wording. Let's just go for the A, B, C, D. What would be the integral from pi to 2 pi? Nope. Nope. Negative 2. Why? Uh-oh. We have to write down the graph of. They've given us. Is it red? Is it blinking? Oh, hi, all my friends in the last 2 minutes. Just kidding. Drama queen, drama queen. Oh, you missed it. Okay, Ethan. Okay. They've given us this. Done. Okay, they want that. Okay, it's that, just underneath. Okay, cool, negative 2. Woo! How about this one? 0, because it's the above and the below, and they cancel out because of symmetry. True? How about this one? 1? How do you? Oh, because of symmetry, it's half. Awesome. How about this one? Isn't that just going to be a rectangle? This gets bumped up, and then what's underneath? Think about a little house. Right? If you shift this guy up, there's going to be a little area that he's got shifted up by, and that little area is going to have a height of 2 and a width of pi. 2 pi plus your 2. There he is. Not times 2. Just leave it and be, yeah, something. Okay, how about this dude? 4 pi? 4. Good. Check it. You know integrals. Pull out the 2. 2 times 2 is 4. How about this guy? 2. But I always like to think of u-bounds. U-bounds. What if u is x minus 2? Right? Then that'd be sine of u. Then my u-bounds, couldn't I plug pi plus 2 minus 2 and I would get pi? I could change this integral to be x minus 2. 2 minus 2 is 0. Pi plus 2 minus 2 is pi. Sine of u d. Okay, well that's a little tricky. But if the derivative is, sorry, if u is x minus 2, du is just 1, right? We haven't talked about that in a while. Anyway, what's this the same thing as? 2. How about this dude? u bounds. What's 2 pi over 2? Oh, pi. What's 0 over 2? Oh, 0. Sine of u. Wouldn't that be 1/2 du if I took the derivative of both sides? I'm cheating just a little bit. But didn't this guy just get horizontally stretched by a factor of 2? Stretched by a factor of 2, right? Horizontal on the inside. Huh.
What's the formula of the period again? The period of this line.
Oh, period. So I take my inside, which would be 1/2, and then I could go ahead and plug it in. So that would end up being 4 pi. So it takes 4 pi to complete what 2 pi is, right? And then I got stretched from 0 to 2 pi, which would, I don't get why my area is smaller, not bigger. Because right now, according to my math, the area would be 1. Is that true? Sure. I think I disagree with myself. Ponder that one for a second. But for this one, cosine. Oops.
0. Yeah.
Not that. It's okay. Smartboard and I are just not on the same path today. Path, link, something. There we go. 0 to pi, it's going to be 0. Right? Because the above and below. Anybody find a mistake in my last one? Oh, it was 1/2 dx. Thank you. So then 2 du. I was going to say it needs to be bigger, not smaller, because a stretch would make the area long. Thank you. That'd be 4. Because du is equal to 1/2 dx. I just was trying to do mental math when we haven't been doing this recently. That'd be 4. Or just think horizontal stretch by 2. Oh, hey, the whole thing got doubled. Okay, so that's playing around with what if they give you one fact, what if they give you one detail as far as one particular area, and then can you use it to find a lot more? Yes. Properties of definite integrals. We just use some of them. If we have a constant function, aka if f of x, and maybe I should have stated this, if f of x is equal to c, that's going to be that nice little oh, hey, it's just going to be a constant, for instance, like velocity, to where the area is just going to end up being my b minus my a times my c. It's just going to be a rectangle. But you could go ahead and solve it. Cx, oh, we haven't learned the fundamental theorem of calculus yet. Accumulator function, he's that guy that they love to take derivatives of in APs, like ddx of a to x or ddx of a to u. And they love to force you to deal with that, the accumulator function. They're not giving a set upper bound, they're letting that upper bound move and change. Anyway, just reminding you of that name. What if the upper bound isn't a constant, but instead an x? And then there's this idea of, we said all continuous functions are integrable. All continuous functions we can find area, or there is like a set actual existent area underneath. That doesn't mean there are no discontinuous ones that work. Some discontinuous ones work too. For instance, let me show you a basic discontinuous one. What if I was to give you something like f of x is equal to the absolute value of x over x? You guys should be used to this one. Isn't this the derivative of absolute value of x? And doesn't he look something like, oh, hey, on the negative side, they're all -1. On the positive side, they're all +1. But at 0, he doesn't exist, because 0 over 0, even though in limits, we would still go looking 0 over 0 with a DNE. What if I wanted us to find, for instance, an integral the non-existent point does nothing to detract from because it's infinitesimally thin, aka there is no depth, does nothing to subtract or detract from the area. So I could go from -1, I can make a little baby rectangle, and I could go to 1 and 2 and 3 and make a rectangle. This discontinuous sliver in time does nothing to take away from the area. I could still accumulate the area, and it would still exist, which is weird. Now technically we shouldn't leave the integral written like that because it has you going through 0, which is a non-existent point. But technically we could still find that area. And to be honest, well that's just a 1 by 1. So that'd be -1 plus, and that's a 3 by 1, which would be 3. I'd end up getting 2, even though there's a discontinuity in the middle. We'll talk more about improper integrals after we cover a lot more integrals. So that brings us up to basically practice example problems. I want to zoom in. I'm afraid I'm going to leave people behind. Is anyone still writing the notes? Nope. I think a couple of you are, but you're being very gracious, so let's just play with homework help. Yeah? Express as a definite integral, then evaluate. Find the output. What a pump is pumping out if that's how fast it's pumping out. Wait, if that's how fast, isn't that a constant rate? What would my integral look like? 0 to 60 because minutes. 25 dt because of time. True. But wouldn't it be as easy as, oh, it's a constant 25 with a length of 60. Dun, 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 gallons. Okay. That's without even taking an antiderivative. That's just knowing that a constant rate will get me a nice pretty rectangle. How about the next one? Write the accumulator function as a polynomial. Guys, you've already learned antiderivatives. True. We haven't fully learned the fundamental theorem of calculus, but I'm sure they talk about it somewhere in the section about how to do the accumulator function. Don't we know that we can go ahead and plug it in, right? 2t squared over 11tx squared. But we don't just have the top bound, don't we also have the bottom bound? Which would be 5 times 1 minus 2, nope, minus 1 squared. I know it's a little bit nasty. I went ahead and 5t minus t squared plugged in my top bound and my bottom bound. But this would be a polynomial, more specifically what, minus 4? It'd be 5t minus t squared plugging in x and plugging in 1, right? 5 minus 1 is 4 and 1 is 4. Go ahead, what's on? Oh, I was like, I'm pretty sure. Okay. What's going on next? Wait. How do I integrate? Huh? This is a step function. Who's this? Isn't it an x plus 2 with a hole at? I can't find that because the hole smacked out in the middle. Does it make a difference? No. Because the hole, that vertical line, has no depth. Can I still go between 0 and 3 even with a hole? A hole, because this is the same thing as x plus 2. A line with an intercept of 2 with a hole at. Alright, okay. You might have to review the step function, but it's a basic graph on your forever part.
That was my play all of it. I have otter. Yeah.
The baseball is canceled, please set your
Bye guys.